Let's study 9th Standard ICSE Physics, Chapter 3, Laws of Motion. Today we'll be studying 3E. So, the universal law of gravitation is denoted by this equation, F is equal to capital G m1 m2 upon r square. The reason why it is called universal is because this law is applicable not just on Earth, but everywhere in the universe. So whatever research has been done so far indicates that this law is true even beyond our solar system or beyond our Milky Way. This was a fascinating discovery because gravity is something which is taken for granted. When things fall down, we know that the Earth is applying a gravity on that object, a gravitational force on that object. But it is the same force which is responsible for the revolution of the moon around the Earth or the revolution of the Earth around the sun and many heavenly movements. Now, experimentally it is shown that this gravitational force is directly proportional to the product of the masses, that is, heavier the objects, more is the gravitational force between them. Also, as already discussed, the gravitational force is inversely proportional to the square root of the distance between them. More the distance between two objects, weaker is the gravitational force. If we combine these two proportionalities together and we replace the proportionality sign with an equal to sign, then we have to introduce a constant of gravitation. And experimentally, we have calculated the value of capital G, which is called the universal gravitational constant. It comes up to around 6.67 into 10 raised to minus 11 Newton meter square per kg square. Minus 11, this order tells us that gravity is extremely weak compared to other forces like magnetic force, which is around more than 100 times stronger. This gravitational force on Earth is also called the weight of the object. So the weight of this marker, let's say, is 1 kgf. This means that the Earth is attracting this marker towards the center of the Earth with a gravitational force of 1 kgf. So kg is a unit of mass, whereas a unit of weight is kgf. And that is not the SI unit. The SI unit is Newton because it's a force. And the SI unit of any force is Newton. More about it shortly. But let's study some characteristics of the gravitational force. It is always attractive. We have not discovered any repulsive gravitational force or anti-gravity yet in real life. Next, it is significant only between huge objects like heavenly bodies. We don't discover gravity's influence between small objects like the marker and the book. Although there is a gravitational force between them, it's too small to notice with naked eyes. And the interesting thing is that though the Earth is attracting the marker towards its center, the marker is also applying an equal gravitational force on the Earth. The marker is also trying to attract the Earth towards itself with the same amount of force, 1 kgf, although in the opposite direction, that is the upward direction. Then why does the marker move? Why not the Earth? Well, that's because, first of all, 1 kgf force is not enough to move Earth. Earth is too huge. And secondly, Earth is surrounded by objects everywhere on its entire surface, each of them trying to pull it in different directions, so they almost nullify each other. And they are very weak indeed. Only a very huge object like the sun or the moon can influence Earth through gravitational force. Now, this universal gravitational constant can be defined as it is equal to the gravitational force between two masses of 1 kg each and separated by a distance of 1 meter. Now let's understand the concept of acceleration due to gravity, which we have already studied in chapter 2. Imagine an object falling from a great height, from a terrace of 20 floors. Initially its velocity is 0 meters per second. After 1 second, its velocity will be 9.8 meters per second. After another second, its velocity shall increase to 19.6 meters per second. And after the third second, it will be 29.4 meters per second. So the velocity keeps on increasing. And it is increasing by a fixed amount, a fixed magnitude, which is 9.8 meters per second every second. Hence, it's a uniform acceleration, at least for the surface, the area near the Earth's surface. And that is called acceleration due to gravity, which is approximately 9.8 meters per second squared. It's an approximate value because the value of G differs at different places. Near the equator, since the Earth is bulging, the value of G is slightly less because it is far away from the center of the Earth. So the gravity is slightly weaker. At the poles, since the object will be closer to the center of the earth, the value of g is slightly more, let's say 9.83 meters per second square. Also on top of mountains, as well as deep inside the earth's surface, the value of g decreases. So the value of g is maximum at the earth's surface, and that too at the poles. When an object falls in vacuum, then the value of g is 9.8 meters per second square. But in reality, since we have friction due to air, there might not be an acceleration of 9.8 meters per second square. So different objects may fall at different rates. That is why a heavy object like a rock will reach the earth's surface first compared to a feather. But in the absence of air, if you drop a feather and a solid object like a rock or a ball, then they will have a free fall without any friction, and both of them will reach the earth's surface at the same time. This has been experimentally proven. Also, let's understand the relationship between small g and capital G. Capital G is a universal gravitational constant. Its value is the same everywhere, whereas value of g is not the same everywhere. On Earth it is around 9.8. On the Moon it is less, 1.67 meters per second square, because the gravitational force on the Moon is just 1/6 of that of the Earth. On Jupiter, the value of g will be far greater than that of the Earth, because the gravity there is very strong, because it's heavier. The relationship is derived as follows. First of all, the gravitational force on any object is nothing but the weight of the object, and the weight of the object is m into g. That means that if your mass is, let's say, 50 kg, then we say your weight is 50 kgf. If your mass is 60 kg, we say your weight is 60 kgf. So mass and weight are different concepts. Mass depends on the total number of atoms in your body. It's the quantity of matter in your body. Your mass remains the same no matter where you go. If your mass is 50 kg on Earth, it will be 50 kg even on the Moon. But the weight depends on acceleration due to gravity also, not just the mass, but even the gravitational force acting on you. So if your weight is 50 kgf on Earth, or 500 Newton on Earth, on the Moon your weight will be just 1/6 of that. And in space, in the absence of significant gravity, you will be weightless, you will be floating, zero weight, because g will be 0, so your mass into 0 is 0 weight. So you see, weight is a vector quantity and mass is a scalar quantity. Weight changes from place to place. Weight has a direction, it's a gravitational force, so it's directing downwards towards the center of the Earth or any heavenly body. Weight is measured using a spring balance, whereas mass can be measured using a beam balance or a physical balance. So if you want your weight to be calculated in SI unit Newton, then mass is 50 kg and g is 9.8. Let's take it as 10, let's round off to 10 meters per second square. So your weight is 500 kilogram meter per second square, that is 500 Newton. That's your actual weight. So the next time somebody asks you your weight, you know how to respond. So the gravitational force, that is a weight, is mg, but we know that the gravitational force can also be calculated using this formula. So let's substitute this formula out here, where capital G is the constant, capital M is the mass of the Earth, small m is your mass or the object's mass, and capital R is the radius of the Earth, because that is the distance between the object and the center of the Earth, which is the origin, or considered as the origin of the gravitational force of the Earth. So small m cancelled, cross multiply, just flip it and we get this equation. G is equal to capital G into capital M upon R square. We know G's value, we know Earth's mass, and we know the radius of the Earth. Scientists know it, and after substituting the values, it is indeed found to be 9.8 meters per second square. And you see, in this formula, small m is not there, which means acceleration due to gravity does not depend on your mass at all. It only depends on the mass of the planet and the radius of the planet. So now we can calculate the value of g of any heavenly body, Jupiter, Moon, etc. All we need to know is the mass of that planet and the radius of the planet, which scientists can calculate indirectly. Next, let's talk about the units of weight, which I've already discussed. The SI unit of weight is Newton, although we can use kgf and gf as well. So what's the relationship between kgf and gf? 1 kgf is 9.8 Newton, which is approximately 10 Newton. So you can see that the definition of 1 kgf or 1 kilogram force is the gravitational force exerted on an object with mass 1 kg. And 1 gf is defined as 1 gram force is that gravitational force exerted on an object with a mass of 1 gram. Now these units can be used not only for the gravitational force but any force, because now we know the relationship between GF and dyne as well. 1 GF is equal to 980 dyne. Everybody knows this. 1 GF is equal to 980 dyne. So if you are holding an object of, let's say, 100 gram on your palm, what is the weight of that object that is a marker? 100 GF downwards. And your hand is applying a normal reaction force upwards, which is also 100 GF, or you can say it is 0.1 Newton. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.